device suggests is based on the architecture resistive random access memory. So the main mechanism of this device is resistive switching. We change the resistive states of the device to write the information or to erase the information. What we discover is that we have four types of different mechanisms in order to save the information. Firstly, the first region A in the plot B is a thermion emission limited conduction. Why is this happening? Because when we probe the device and we apply the voltage, some heat is generated. Region B is ohmic conduction. Then we have space charge limited current, and D is trap charge limited current. So how does this device work? Is by trapping and detrapping of charges on our surfaces. Another most important feature which we wanted to achieve in this research is parallel processing. How we can achieve it here is through something called multi-level per se storage characteristic. This characteristic allow us to store more information per one bit because we have multiple resistive stages that we can save or erase the information, which in this case we have 5, which allow us to process the information in parallel manner because I can store or erase information by different resistance level of our devices, which is extremely important for the tasks like machine learning or artificial intelligence or even for future computing processing. Because instead of like normal CPU, one task at a time, this can work like GPU, multiple at the same time. In our first publication by using topological insulator, we were also able to emulate the true neuromorphic behavior, synaptic plasticity. We are able to emulate spike rate dependent plasticity. Is a Hebbian rule which allow us to train and teach our device some new things. We are able to emulate paired push facilitation and post-enhancing potentiation, which are the form of short-term potentiation. So this device has a capability of the short-term memory, like in us in human brain, and have a capability of long-term potentiation, the long-term memory. So for example, I'm Polish. So if I would teach you guys the Polish word hello, which is dzień dobry in my language, most probably after 2-3 minutes you will forget this one, and that's a short-term memory. But if I will tell this word for you for every day for a period of 1 month, then you will remember this for a longer period of time. By allowing to emulate this synaptic plasticity, this functionality in the device, we can teach the device itself without connecting the computer to process the data, to analyze this and process it. I can teach the device to remember, let's say if the current goes to the level of 2 milliamps, this means something. I can teach the device in this way. Additional way, what we actually achieve in this device, and this is shown in the figure G, H, and I, learning, forgetting, and relearning capabilities. So we proved that this device can learn something, this device can forget something as a human being, and relearn something, which learning process, what we prove, is much easier. The same way us in humans, when we learn something first time, and after 2 months we are trying to do it again, it will be a bit easier for us to recall this information, to recall this knowledge. That's what we can achieve in neuromorphic devices, in neuromorphic hardware. And why is this so important for the future? Is because it will allow us for ultra low power consumption, high processing speed, parallel processing, the three things which soon will end in our normal architecture due to the von Neumann bottleneck. Because nowadays in computers, as I said before, when we want to do something, we need to fetch the data from the memory to the CPU. And that's perfectly fine when there is a lot of data. But when the data appears more and more, the latency, this bus which go between those two units, are slowing down. That's why we wait sometimes. Using neuromorphic computing and neuromorphic hardware, it will not happen. That's why this is a promising architecture for the future. As a proof of concept, we developed our topological neuristors. We call this device a neuristors because it's emulate like neuristor behavior. We train two devices. We train two bots, robots. What is game rock, paper, and scissors? Without connecting this to the computer, those devices were able to play simple game rock, paper, and scissors and understand who lose and who wins. We achieved 99% of the accuracy in gesture detection and the winning score as well. Another important field which is promising right now is to create a brain-computer interface, similar to something what Elon Musk is doing with Neuralink or with the robotics power. We can use a neuromorphic device, which is also called artificial synaptic device, which is a perfect fit for brain-computer interface. In another publication, we use the bismuth telluride based topological insulator material to develop a new type of brain computer interface. These devices, which are based on the topological insulator, are a perfect fit for brain computer interface. What we actually did here is we create our neuristors, same as before, but we use this device not for normal processing, but for neural processing. What we wanted to achieve is to create a neuromodulator device with the capabilities to detect and enhance the neural signal. What is the application of this is a get-on technology. Get-on technology is technology which helps elderly people, especially we target cognitive function losses like in Alzheimer or Parkinson's disease. So this device can be implanted into the human work without any connection to the computer or anything. This device can detect the signal, enhance the signal, okay, and reconstruct it, because I will show in later slide. When we have a teenager, his EEG is extremely sharp. There are big peaks. But in when we get older, our EEG gets more smoothened. Why? Because the synaptic connection in our brain getting loosened over time. That's why we forget to things. We are tend to forget faces. They are beginning of dementia, Alzheimer, or Parkinson. By using neuromorphic devices, we can not fully change this, but we can slow down this process. How we are doing this is by emulating spike time dependent plasticity. The signal in the brain are sent through the spikes. So if we are able to emulate this spike, which are based on the time, right, we can prove, as in seen in this slide, that by changing the time in which I'm sending those multiple pulses, I can increase or decrease the efficiency of the synaptic connection. What that means that is I can neuromodulate the synaptic connection. If I can neuromodulate the synaptic connection, I can increase the short-term plasticity, which means short-term memory, to long-term memory. So I can increase the time that the brain can memorize things. This is the basic application of our device for brain computer interfaces. Oh, coming back here. There is a parameter in this field which tell us how efficient is our synaptic device, how efficiently we can neurostimulate something. This is called pair push facilitation, PPF index. Here I would like to show the comparison of other different synaptic devices or artificial synaptic devices or neuromorphic devices which are also able to neuromodulate, but their efficiency cannot cross PPF index of 200. In ours, topological insulator, we cross the level of 210, which is extremely efficient. There is another parameter called post-tentative potentiation. It's a longer version of the PPF, of the short-term memory, which also shows here that we can emulate this in the high efficiency with the PPP index, PTP index, or PTD index of 240 or 230 here. Those levels of the efficiency are actually possible through the ability of our materials. Because of the surface state, we can achieve a high neuromodulation possibilities with ultra low power consumption in the level of the picojoules and high switching speed as well. Here is the representation of how we can switch from short-term memory to long-term memory. This is the proof that our device, let's say in this case we have in seconds, okay? That our short-term memory is 2 seconds. So this device, when you teach this something, will remember for 2 seconds. After sending precise pulses at the specific time and at a specific voltage, we can increase the short-term memory to long-term memory, as you can see on the left side. The same is on the right side, which is representing that we can extend this. Here is just in seconds, but we can also prove this in hours or even weeks, which allow our device to remember the information for a longer period of time. Here is a proof of concept which we developed and did in our team. So how does this device process actually works is that we first of all accumulate the EEG from the human brain. From this EEG, we extract something called event-related potential. Event-related potential is extremely important in a cognitive function because there are different peaks, like can be seen on the image, peak 1, peak 2, peak 3, like P300, P200, P100, N100, and 200. All of these different peaks correspond to different things. For example, peak 300 is for learning and memorization. Peak 200, I think, is for motoric capabilities of the human. So by accessing the information for a particular peak, we can see which function of the human brain does not work as in the young brain, as it was like, let's say, 20 years ago. This information is fed to our synaptic device array through the PWM encoding, pulse wave modulation. In this, we also develop our own index telling how much there is a difference between young brain and the old brain. Because we collected the sample from the brain from the age 20 to 30, then from 40 to 50, then from 50 to 60, then from 60 to 70, and 70 to 80. And we see the difference in peaks. By analyzing this difference in the peaks, we can train our device how much we need to restore the signal, how much we need to enhance it, how much pulse we need to send with specific timing or specific voltage to increase this signal back as it was by using in the young brain. And then we can use this for controlling different brain-computer interface or machine-computer interface, this kind of application. So the main reasons in the neuromorphic field, actually there are three main applications for this. Brain-computer interface is one of them. Second is ultra-low power consumption processing and parallel processing. Those three main fields are allowed using the neuromorphic computer, and that's what we are actually aiming for. And